Hello there, this is Durwell King with ELC 113, and this is August the 26th. I'm recording this on Wednesday, pre-recording it for y'all. And today we're going to go over chapter 2 in our book. And for those of you, if you don't have the book yet, it is an excellent book, and I would make the investment to get it. House Wiring, 5th edition by Greg Flesher. And as far as I know, there should be some in the bookstore. I haven't checked this week, but if you go over there and if they happen to be out, let me know. We can reorder, or you can get them online. But we do encourage you to buy them on campus to support the school. But it is an excellent book. It is worth more than you'll pay for it. It's a lot to get it, but it's worth more than the dollar amount when you look at the money you're going to make in the long run, and it's going to help you to enable you to make a better living for the rest of your life if you use this. So anyway, I'm going to flip over and start immediately here in our book. And for those of you that don't have the book yet, I scanned a copy of chapter 2. Uploaded it into Moodle, so you can download chapter 2. Now, I'm not going to do it beyond chapter 2. I'm not planning on scanning. I can't scan every chapter legally. So, but I did do chapter 1. Chapter 2 is done that way, and so you can get the book copy for now if you're still waiting on getting the book. Right there in week number 2 in Moodle, just go to week 2, and you'll see in there the scanned copy of chapter 2 and the link for this recording. And then after I finish recording this afternoon, I'm going to go in and put the worksheet in Moodle. I've got to convert it from a paper copy, paste, and do all that stuff and get it in a Moodle format. I haven't done that yet, so it's going to take me a while. But later in the evening, I'll have the worksheet will be in there that you can begin on whenever you get time. And try to stay on top of your worksheets, reading the chapters and doing worksheets. Don't let it pile up toward the end of the semester. It's going to make it hard on you to catch up. So, and let me know if you have any questions about the chapter, about these recordings, and you can either call me, text, or ask me questions when we're in the shop, and that'll be fine. Okay, so we're going to go right on ahead and get to it. Okay, so in its chapter 2, hardware and materials used in residential wiring. We start out by looking at nationally recognized testing laboratories. The National Electric Code that we go by states that the authority having jurisdiction, and that is your local county electrical inspector. For us, down behind Dairy Queen on Rowan Road, if you go down that road, go down a little ways to the county complex, take a left and go in that complex, and there is our county electrical inspections office is in that complex. And that is, there are several guys in there. There's 2 electrical inspectors that I know of, and they are considered to be the authority having jurisdiction in Sampson County. So if you go to do a new electrical installation or an add-on, you go out there to those, and they call it an AHJ, authority having jurisdiction. You go out there to the electrical inspector, and you request a permit to do a particular job. If it's a new installation, wiring a house, doing an add-on, or whatever it is, if you're a licensed electrician, you would go out there and pay for a permit and talk with them about the job you're going to do, get in the details, make sure that they're okay with the way you're going to do it. You go do the job and then tell them you're ready for inspection. They come inspect, they sign off on it, and then you're legal, you're covered. So that's the way, that's who the AHJ is. So the local inspector in Sampson County, those guys would be ones that would tell you if certain materials are approved in this area or not. So, and just to kind of give you an example of where it could be different in Sampson County is than it could be maybe at the beach. I have heard that Certain locations at the beach that you're not allowed to use, regular Romex cable and doing it on, stapling on the studs. I've heard that down there, I guess maybe on condos and all, that they're having to put their wiring in conduit instead of having it like this, just a flat non-metallic cable. So it depends on where you're at as to whether you're allowed to use certain materials or not. Up here you don't have to wire a house and put conduit in there. You're stapling the Romex non-metallic cable, stapling that to your studs. But again, depending on where you are, you may be required to have conduit or flexible conduit in an apartment or condo or something down at the beach. I have heard about that. So many inspectors or AHJs approve their equipment based on whether it's listed by a testing lab, a national recognized testing lab. And these testing labs, they will test a product before it's allowed to go on the market, and then they'll put their stamp on it. And there's several labs that we're going to look at here. The main one in the United States is called UL, Underwriters Laboratories. And there are other ones, the CSA, Canadian Standards, and then there's ITS, Intertech Testing Services. But UL is the main one that you would recognize stamped on products that you go and buy. If you go buy a television or go buy whatever, a power tool, anything you go out and buy, you're going to see one of these testing labs stamped on there, at least one, and you may see multiple on there. So the UL symbol you see on there, with the U and the L like that, that's their stamp. And you'll even see that stamping on things like, multimeters, for instance. I'll show you on the back of this meter, like you're using in class. I'll show you where the UL stamp is. I'm going to hit stop screen share, and here on the webcam, let's see if we go this way. So if you notice right there, you see the UL classified stamping on there. So this meter has been inspected by Underwriters Laboratories and by the CSA, the Canadian Standards Organization. So it's been approved in the US and in Canada to be a safe meter. Okay, that is, of course, made by Fluke. They're top of the line. But that just gives you an example. And whether it's a meter, whether it's a TV, or whether it's a refrigerator, anything out there on the market that's electric is supposed to go through a testing lab before it's put on the market. They test it to see, is it going to be, does it meet the ratings that it's rated at, and all that. Okay. Go back to our book. Underwriters Laboratories, they got a directory that you can download. It's called the White Book, and you can go online to their site, and that White Book is going to be like a comprehensive guide book that tells you, that lists every product that they inspect, and tells you, it just shows you everything information on everything that they rate. And that's giving you the download site there. It's also in your book. And that's just a snapshot of the UL product spec web page. The CSA stamping that you saw on the back of that multimeter, that's the Canadian standards. Then we move on to a variety of electrical boxes that we use in residential. And there's a lot of different styles, sizes. ways that they can mount. This one here has a side bracket that easily makes it that you can put it onto a stud and nail. Very convenient. There's a lot of different dimensions on boxes. Those metal boxes, some of those the sides can be removed with a screwdriver, and you can attach those together to expand them into into a 2-gang, 3-gang, or however many gang you want to have in there, and design your own box width. If you're going to have a lot of switches in a room, like in a cafeteria or something like that, you got lots of switches in there, you can gang those together and have your own customized box set up. Here they're showing pry outs and knockouts. Pry outs, you can pry those out with a screwdriver. Knockouts are, well, the pry outs are used to fish in your cable such as this. And once you get inside the box, if it's that type of a metal box, then there's a cable clamp down in there that you would secure the cable with. And then knockouts on the side, they're round and they're pre-punched. You just knock those out with a screwdriver, and they're going to be different sizes for conduit, or for Romex connectors that are clamp type connectors. So the knockouts are going to be for box connectors of various kinds. The grounding screw in there, the 3 for it is a 1032. So that you obviously need to ground the box if it's metal. You got your mounting ears that are there if you're going to mount it, say, in sheetrock. If you're doing an installation in an existing wall and you're going to do a cutout in sheetrock, then you can use those mounting ears there for mounting it. Here you have one called a handy box. It doesn't have mounting ears or anything, and that's going to be usually used for surface mount applications, like maybe in a in a workshop outside, or anywhere that you're going to have a surface mounted box. You're not going to try to have it recessed, and it can hold one device like a switch or receptacle, and they call it a handy box or a utility box. Here you got a variety of PVC boxes that can be nailed onto the studs, 1 gang, 2 gang, 3 gang, so on. Very inexpensive. They can be made out of PVC, phenolic, polycarbonate. This is one that it's going to cost you more to get these. These have a slide-on bracket that slides right over on the front of the stud, and it's going to make it faster to do install. So if your contractor you're working for, if he's shooting for speed, he may spend the money to go buy those, and you can just slap them on there and go on. If he's one, and the faster you get a job done, the more profit there is for him. He's getting paid by the job, you're getting paid by the hour. Outlet boxes, they can be used, for lighting or access to power for appliances and things. So an outlet box simply means it's a place that you're going to get power from, and you may or may not have a device mounted to it. It may be just an access point to get power for a device. They got different shapes. You can have the PVC, the metal, and they got different ways of mounting them. Some of them have brackets built onto them and some don't. Some are octagon, square. There's a lot of different dimensions of those boxes you can get. The covers for these boxes, there's a wide variety of those. Some of them are raised plaster rings. Depending on your mounting needs, there's a variety of covers and rings that you can use on the front of the boxes. All of those are going to be by your 4-inch by 4-inch boxes, and so that just shows you that there's a huge amount covers and plaster rings that you can have to give you your mounting requirements. What I would recommend is anytime that you go to Lowe's here in town and you have extra time, go down the electrical aisles and you look really good and just see just how much that we do have here in town at Lowe's. We're blessed to have Lowe's, and there's a whole lot in there. Just go through there and find out what's actually here in stock, and you'll be surprised how much is in there. There's a tremendous amount of detailed parts in there that you can walk right in there and buy that don't have to order, including stuff like this. These are junction box covers. They're just flat covers that when you're going to have, when you're going to splice wires together in a box and you're just going to, but not a device in there, that's just going to be a flat cover. So, that'll fit those 4x4 boxes that we just looked at, One thing about junction boxes is you cannot have a junction box concealed in drywall where it's not accessible. A junction box has to be accessible for service and for troubleshooting later on. So you've got to be careful where you choose to put a junction box. As far as in a house, you would have to put it in the attic or under the house or in some area where it could be accessed. Special boxes that are for heavy duty applications like heavy duty ceiling fans and so forth, those boxes will be rated at a certain load, that they can hold a certain load with the screws and the threads and all in these boxes would be able to handle these larger ceiling fans. So you have to look at the ratings on, on the boxes that you're hanging things from. Now on conductors, wires, they're usually in an assembly, like we have here, that you have a non-metallic sheath cable. You got your conductors that are in there. Most of the time in residential, you're going to be dealing with copper, just with copper. As you can see there, nice and shiny gold look to it, copper. Now, aluminum, you may see aluminum used for a service entrance coming to your house possibly, or you may see it commonly used as your main service entrance for your workshop outside. So if you run power from your house to a sub panel out in your workshop, people typically will buy aluminum wire instead of copper because it's cheaper. And so aluminum, is usually used for, utility buildings and things like that. Copper clad aluminum is a mix of copper and aluminum. Copper is a better conductor. If you go aluminum, then the AWG size is going to be a larger size to carry the same current that a smaller copper wire will be able to carry, because aluminum has more resistance to it in ohms. But and we'll look in just a second to do just to show you the difference in the amp capacity of aluminum versus copper at a given AWG size. Well, I'll just fast forward to that now. I'll fast forward and show you the chart and just give you an idea, comparing apples to apples here. Okay, now, if we say, for instance, the smallest aluminum conductor that I see on this chart here would be, now the aluminum and copper clad aluminum are in the right 3 columns. Copper is in the left 3 columns. So if you go over in the aluminum area and there are 3 columns, there's a 60 degrees Celsius, 140 degree Fahrenheit column. And what that means is that column is going to be for residential. You got to stay in that 60 degrees Celsius column, the rating on the insulation and the rating on the terminals that we're trying to. So the limitation in residential, you have to stay in the 60 degrees Celsius column because of the terminal ratings of what you're tying to, the screw terminal ratings on the devices, and the cable itself. Now, the cable, you may see the cable rated higher than 60 degrees Celsius. You may see it rated 75 degrees C. But if the terminals that you're tying to, if the screw terminals are, that's where the limit's going to be. So in residential, even though the cable may be rated higher, everything's got to be in that 60 degrees Celsius column. So when you get into industrial wiring, commercial and industrial, you're allowed to use the 75 degrees C column or the 90 degrees Celsius, because the insulation on the wire that we're using in commercial and industrial, the insulation is rated higher in temperature, and also the terminals can be rated higher in temperature. So that's what it boils down to, is you got to have the terminals on each end of the wire, and the wire has to be rated at a particular temperature to be able to use the amp ratings in those columns. Okay. They go off of the weakest link in the circuit, including the terminals that you tie to. Okay. So on aluminum, just for instance, if you take the first aluminum one that's listed here in the 60 degree column, would be a number 12, a number 12 AWG. And just to show you, a number 12 has a yellow jacket when you're dealing with our residential wiring, and it's obviously, it's a heavier wire. So number 12 in copper wire is good for 20 amps. If you notice, if you see where my mouse is, that number 12 wire, if you follow it over to the aluminum, is only good for 15 amps. So it's 5 amps less capacity if it's aluminum versus that copper there. Okay. So that's just showing you that aluminum doesn't have the amp capacity or ampacity as copper. It's okay, but you have to step up, excuse me, you have to step up to a larger size, a larger diameter aluminum wire to give you the same amps that you would get with copper. But even when you do that, you're still saving money because aluminum is just a lot cheaper to buy. When you go to Lowe's, get down there and look at the aluminum. They got it on rolls, and you'll find out that it's a lot cheaper. A lot cheaper at the scrapyard too. If you're selling scrap aluminum or scrap copper, there's a huge difference in price. I think scrap aluminum at one time was like 35 or 40 cents a pound for clean aluminum, to where clean copper, number 1 copper, was about $2 a pound at the scrapyard for selling it. So it's a huge difference in price. Copper is preferred because it has lower resistance, and it has less problems in the long run. Aluminum is softer. In the long run, you may have issues with the terminals being loose. And aluminum also tends to oxidize more. So you got to put an antioxidant compound on the aluminum wire when you put it into the lugs to prevent oxidation. If you leave something aluminum out in the weather, it's going to develop a crust on it, on the surface of it. It doesn't mess the aluminum up, but it's just on the surface, and that's what can happen with electrical connections that are aluminum. But they make a compound that prevents that. This is a handy chart right here in your book that you could, you might want to take pictures on your phone. I would recommend going through and taking snapshots on some key things. But here it tells you if you have something like a receptacle or a switch, 15 or 20 amp rating, and you see the markings CO or ALR, if you see those markings on the device, and where you'll see it at on the device would be I'm going to show you on a switch the abbreviations that tells you if you're allowed to put copper connection only, or if you're allowed to do copper or aluminum. It actually tells you right there on that device. Let's switch over to the camera. Now, if you look here, let me adjust the focus here. That's good right there, very good. And if you notice there, what does it say? It says use solid copper or CU clad, copper clad wire only. Use copper or copper clad wire only. So you're not allowed to use aluminum on those terminals. You're not allowed to use it by the requirements of the company that made this, by UL. Do you see that UL on there? There goes UL again in the United States. So here we go. This switch was rated by the company that made it, and it was and then UL gave the approval in the US that we have to follow those guidelines. Okay. So it would be, I've never seen aluminum wires that would tie to these. I've seen it for large feeders for going into panels, but that just gives you an example of how detailed the ratings are on these devices. It tells you, if you look close enough, it gives you a lot of detail what you can and cannot hook to it. The inspector, and I'm going back to the book here, the inspector that comes to inspect the job, they know a lot. All they deal with is codes and inspections, and they can spot things like that. So anyway, if you don't see any marking on there as far as restrictive, then you can do copper or copper clad aluminum. But if it says CO or ALR, the ALR will be aluminum, then you would be allowed to hook aluminum to it, or copper clad aluminum. If you're dealing with 30 amp or greater receptacles and switches, and it says AL, that's aluminum, CU is copper, then you can do any of those. If you don't see a marking, then it's copper only on 30 amp or greater devices. And then so on. For wire connectors like wire nuts, crimp connectors, lugs, these markings, the AL means aluminum and the CU means copper. You know, CC, copper clad, and so on. And one thing, let's see, there was down here, I think there's a typo in the book. So if you have your book or your download, down in here where it says copper only, the CC should not be in there. That's like copper clad. That should not be in there for copper only. Okay. Conductor sizing or wire sizing, they are rated on by the American Wire Gauge System, the AWG system. And for residential, you would typically have from a number 14 AWG up to a 2/0 copper. 2/0 means 2/0. And the alt is an old English term, AUGHT. Now you can see it's smaller than number 14 on some lighting fixtures. Some light fixtures, the wires may be a number 18 smaller. But that would be something included on the light fixture itself. When you're dealing with only a, you know, like a 60-watt bulb, then the manufacturer may use something smaller than 14. And your 2/0 would be larger, like your service entrance wires. The larger the number, the smaller the conductor you're going to see on this wire chart. The smaller the number, the larger the conductor physically in the AWG ranges. So let's fast forward to that to see the example. Physically, there you go with a number 14 AWG, number 12. So as the number goes down, the wire gets bigger. So as you go from a number 12, see a number 10 is bigger, 8 is bigger. The 8, 16, and all in there, you're talking about like for clothes dryers, for stoves, for welders, these roll around welders that y'all have been using in the welding classes or maybe in your shop, and so on. So as a number 6 is very large, 4, 3, 2, 1. When you get down to a 1 AWG, of course, you know, it has gotten considerably bigger. And then after that point, it changes out of AWG into the aughts, 1 aught, 2 aught, 3 aught, 4 aught. Let's go to the chart and see when it gets to the aught ratings, there are 4 of those, 1 aught, 2 aught, 3 aught, 4 aught. Here, when you get down to a 1 AWG, then the numbers go in reverse. It starts at 1 and goes up 1, 2, 3, 4. And as the numbers get bigger, the wire gets bigger. So I don't know who came up with that system, but it's something that it's established, and we have to live with that. So here on the wire chart, if you look where my mouse is, we start with a number 18 on in the regular electric code book. It goes 18 AWG, 16, 14 is where you start with residential wiring that you can buy to install. 14, you don't buy smaller than that. It's good for 15 amps. On number 12 is good for 20 amps. So nowadays they're color coded. So the tan jacket is good for 15 amps. That's 14. Number 12 is the yellow jacket. It's good for 20 amps. And then the number 10 is the orange jacket, and it's good for 30 amps in residential. On older homes and all, everything might have been a tan jacket in the years before they started color coding. Now watch what happens on, as you go from an 18 AWG and the numbers get smaller, then the physical wire gets bigger and the amp rating or ampacity gets bigger. Until you get down to a number 1 AWG. A number 1 AWG is good for 110 amps. Okay, so that could be like, could feed a garage that has a 100 amp panel in there, for instance. When you get larger than a number 1 AWG, it switches over for these 4 sizes here to 1 aught, 2 aught, 3 aught, 4 aught. And that's where the numbers go in reverse. As the numbers get bigger, the wire gets bigger and the amp rating gets bigger. Then after 4 aught, it goes into a different type of a rating. It goes into something called KC mils, not aught, and not, you don't call it AWG, but it is, all of this is AWG system. But when you get down larger than a 4 aught, it turns into just 250 KC mils. K means 1,000, and C mils, C-M-I-L, means circular mils. And if you're taking the, well, let me just break it down that way. If you're not taking Introduction to Electricity now, or have not taken it, a circular mil is this, okay? Your hair, one strand of hair, real small strand of hair, okay, or fine strand of wire, one little strand of wire on multi-strand wire that's just like hair like. If you had one strand of copper wire that measured 1/1000th of an inch in diameter, if it measured 0.001 inches, 1/1000th of an inch, that's called a circular mil of wire. One strand of wire that the diameter is 1/1000th of an inch. Now, paper, regular paper like this, if I measure that with a dial caliper, paper thickness is roughly around 0.003 of an inch, or 0.003. So if you took a piece of paper and sliced it into 3 pieces thinner than that, if you could do that, you would be down to 1/1000th of an inch. So a circular mil of copper wire is 1/1000th of an inch. Now, this wire down here that says 250 KC mil, and you see the KC mil up in here. It's kind of fuzzy on the PowerPoint. but you can download, and I've actually given you a paper copy of that in the shop. I had it in there last night, and if you didn't get one, remind me, I'll give you a printout of this, and you can also download it off of the Moodle page that we have and save it on your phone. But 250 kc mil means this. Now keep it in mind that one circular mil or one C mil is 1/1000th of an inch, like a little strand of hair. Picture 250,000 circular mils. 250 K means 1,000 circular mils. So you're talking about 250,000 circular mils. And one circular mil is like, you know, a piece of hair, okay? So then you have 300 kc mil, 300,000 circular mils, 350 kc mil, and the largest one in this chart is 2,000 kc mils, which would be this. Those numbers that you see from 250 up to 2,000, you would simply add 3 zeros onto it because it's a K. And so if you add, you know, to the largest one, it's 2,000 kc mil. If you add 3 zeros to it, if you add 3 zeros to 2,000, that's going to become 2 million. 2 million circular mils. Okay, so it's a very large cable, very large. The largest ones I've ever worked with in plants were 1,500. The 1,500 was, I had to have 2 hands to wrap it around a cable that was that big. On welding cables for automatic welding equipment that we had, we had air cylinders that were coming down in production equipment to do large numbers of welds at one time on production welding equipment. So a 1,500 kc mil cable on welding cable, on a flex cable, is about that big around. It's huge. But it's got a lot of small strands in it, and it's flexible like stick welding cable. But you have maybe, you know, 9 or 10 ropes in there of copper wire that's kind of like stick welding cable, and they braid those together into a large cable assembly that can be used on welders. Okay, so now go back up. The ampacity is like the amp rating or amp capacity of a wire or conductor. It is limited by temperature rating of the insulation. So that coating on there has a limit on temperature that you can run it at safely. And also there's a limit. Well, I'll just leave it at that. Okay. Here, this is some typical wire sizes for different devices in residential wiring, and it's going to show you the breaker size or fuse size that you would want for that wire. So this is this is one you should take a picture of with your phone. So if you have the smaller things like doorbell circuits and thermostats and security systems, home automation, the controls on those would be using like number 18 within the devices. And they would typically have their own protection within the device, you know. A 16 AWG you might see on transformers, maybe like on doorbell circuits that step the 120 down to a lower voltage, like maybe around 16 volts for doorbells. Here, we're starting here with what y'all are wiring in the shop. A 14 AWG, for overcurrent protection, you would have to have a 15 amp circuit breaker. So this is a good chart to go by. Snap it with your camera and you'll have it. It's for typical lighting and branch circuits. A number 12 wire, the yellow jacket that we have there, it's good. You got to use a 20 amp circuit breaker or fuse. Now, you're not using fuses in new installations in panels and houses now. On really old panels, they had fuses, these little screw ends, and we'll see that in a little bit in this chapter, called an Edison-based fuse. But the 20 amp circuits would be for typically used in kitchens and dining rooms, laundry receptacles, workshops, small water heaters. As long as a water heater does not exceed a rating of 20 amps, then you could use a number 12. Maybe a half-size water heater, you know, you may see one that may be rated, you know, within 20 amps. A number 10 wire, the orange. Oh, I see Jamie. Jamie's coming in. And this is a pre-recording, but welcome, Jamie. He's logging in. Okay. So I'll give him a second to log in so we can talk some. I didn't expect anybody to join because I'm doing the pre-recording, but I did open it up that you can get in if anybody happened to be that interested. Yeah, Jamie, I see your name there, but I don't see a microphone or anything, so I don't know. You may be on a. Hold on. Let me do a stop share here. Okay, I lost Jamie popped out. Anyway, I'm gonna keep going here. I'm not gonna lag on with this. Okay, so this just shows different wire sizes and the overcurrent protection rating. It's going to be a breaker in most cases, so you would need a 15 amp breaker for 14, a 20 amp breaker for number 12, 30 amp breaker for number 10, a 40 amp breaker for number 8 wire. And you get into those, 30 amp would be for most electric dryers, some built-in ovens, cooktops, central heat and air, some water heaters, and some heat pumps. A number 8 wire is you got to have a 40 amp breaker or fuse, and that's for electric ranges, ovens, heat pumps, some large clothes dryers, large heat and air, and some heat pumps. A number 6 is you got to have a 50 amp breaker or fuse. It's good for electric furnaces, heat pumps, and feeders to sub panels if it's a small sub panel. Now, the nameplate on whatever device that you're wiring into a breaker is going to give you the amp requirement for that device, like for a heating unit or whatever. So if you're wondering on a furnace or whatever, well, how big a wire does it need? You go out to the data plate on that furnace and you get the total amp requirement, you know, right off of the nameplate. And you got to stay within that, you know, for your breaker size. A number 4 AWG is has to have a 70 amp breaker or fuse, and it's going to be for electric furnaces or sub panels. A 3 AWG and larger, you're talking 100 amp breaker, and in those large ranges like that, you're going to be dealing with double pole, you know, breakers, of course, 2-pole like this that has, you know, both hot wires of your 240 device that would be controlled by one breaker. That's you know, it's gained together, you know, with 2. Okay, moving right along. This is the main go-to chart in the electric code book, and I would recommend you having this on your phone and then the paper copy that I've given you in the shop. And we can go over. I think on the recording last week, I think I showed y'all how to go online to the NFPA, National Fire Protection Association, and actually view the entire code book online for free. And so I think that I showed you that last week. Now, this chart in the book gets into the actual types of insulation that you can, different types of insulation that may be marked on your wires or conductors, and it can vary a lot. So letters like THHN, the T would be thermoplastic, and then the two H's would be that it's rated at a higher temperature, 90 degrees Celsius, and the N would be like a nylon jacket. And here you got the W at the end of this one would be for wet location, the W. So all the letters mean something. And those letters will be printed on the insulation of the wire. And if you go back to the wire chart, this is going to show you what column you'll be in. So here you have, in here, THHN, THHW, and so on. So the different letters in there, that's the actual type of thermoplastic or insulation that's actually surrounding the wires. And that determines the temperature rating that you're going to be able to rate that wire at, And here, like on the THHW, they got two different ratings on temperature. For wet location, it's going to be less rating. On dry location, higher rating. So, that wire with a W on there can be used wet or dry location, and then your temperature ratings are going to be depending on which environment you have it in, and so on. So here tells you that the THHN is good for dry and damp locations, has a flame retardant, heat resistant thermoplastic jacket, nylon jacket or equivalent. Those are the wire ranges that you can buy that type of insulation in, and so forth. If you're in a plant or somewhere to where it's subject to wet, then you would have to have the W on the end, and so on. Color coding the individual wires in your conductor. That's a standardized thing across the board. Black is going to be used for hot. It carries the current to the load in 120 circuits, such as light bulbs and things, and receptacles and all. Red is also, the black is considered ungrounded. It's not grounded, and it's considered hot. Red, if you have a red in there, it's also ungrounded and it's hot. And it can carry current to the load in a 120 or a 240 volt circuit. White is going to be your neutral. It is a grounded conductor, not a grounding conductor. So the white, if you have current going out to your load on the black wire, it's going to come back on the white one if it's a 120 volt circuit like this. So here, if you have these three, it goes out to your lights here and comes back on the neutral. The same number of current goes out on the black one. The same amount of current comes back on the white one. When the white one gets back to the panel, all of the neutrals join over through a tie bar to your ground bar, as y'all see in your panels. And the neutral ends up getting connected to ground once it gets back to the panel. You got to keep it separated until it gets back to the panel, and then you let the panel tie bar join these together when it gets to the destination there. So this carries current, the white carries current, but when it gets to where it's going, it ends up getting grounded to the ground wire. Okay. The bare wire here is ground. It's a grounding conductor. Grounding with an ing, to where the neutral is a grounded conductor. Grounded and grounding. Okay. That bare conductor is used to bond all of your metal parts on your devices to keep those at ground potential, to make sure that the metal parts on that device cannot be live or powered. In other words, if you had a hot wire to touch the framework or metal parts on a drill or a light fixture, then the metal parts could become energized and could be a safety hazard, could be a shock hazard if you did not have the metal parts grounded. With a grounding conductor. So the grounding conductor is what goes to the metal parts on all of your devices. Even on your switches, when you hook to a ground here, then the entire yoke, the entire metal yoke on that switch is grounded. Okay, so it's just an example. On motors and fans and things like that, then you have to have a ground there so that the framework is going to be at ground potential at 0 volts, and there's no way for it to be floating at a high voltage. If a hot wire hits it within a device, then what's going to happen is if the hot wire comes in contact with the ground that's on the frame there, it's going to draw a high amount of current really quick when that hot hits that grounded device in there. And what's going to happen is your breaker is going to trip extremely fast because the hot came in contact with ground with no load there. Okay, it just bypassed the load. So it makes a high amount of current really quick, and it's going to trip that and disconnect your circuit. If you didn't have the ground hooked up to the frame on your drill or whatever, or light fixture, if it's metal, if you didn't have the ground there and a hot wire touched the metal parts, then the metal parts on that device would actually be at 120 volt. And if you were to touch the metal parts on that thing like a drill or something, then you could be electrocuted. So that's why ground is very important. It's there for safety. Ground wires can be green when they're insulated, like on the industrial type wiring. In commercial and industrial, the ground wires are not bare like this. They're going to have green insulation on them. Or it could be green with one or more yellow stripes, could be. The difference between ground and neutral is this. Neutral carries the current back from the load. So your black wire carries it to your lights. The white wire carries the amps back to the breaker panel. So they carry the same number of amps, but the neutral gets grounded once it gets back to the panel. The ground wire doesn't carry current at all unless there's an emergency. And the emergency would be that you have a current carrier that comes in contact with the chassis or framework metal parts of a device. And then that current will travel up that ground wire back to the panel, back to earth, and it's going to create a trip breaker, of course. And when you get current on the ground wire, it's something called a ground fault. There's not supposed to be any current on the ground wire, and if you do, it's called a ground fault. Okay. And the ground fault is something that a GFCI picks up on, and we're going to talk about that ground fault circuit interrupter. This knows if you got a ground fault. Okay. Moving right along. This is the first lab that you did, single pole switch, and you notice there that the ground, is hooked to the strap here, the yoke on the switch, and it's not hooked up in the fixture because it's a plastic box. Maybe a ceramic fixture, they're a plastic, and there's nowhere to ground it. If it's got anything that needs to be grounded, you would hook it up. Now that ground wire in there, you don't cut it loose. You leave the excess in the box. So if you upgrade that light fixture to one that can be grounded, like a ceiling fan or something, or a metal fixture, the ground wire is there so that it can be grounded. Different types of connectors that can be used. You've already been using wire nuts, but there's other kinds of connectors. Here you got a variety of wire nut sizes, and the next time you go on the cart to pull out a wire nut, kind of look on. There's a chart on there that tells you, say for a yellow wire nut, it tells you how many wires you can put in there of what size. So it gives you a variety of, you can put so many number 14s in there or so many number 18s in there, you know. And then for the red one, of course, it's going to go up. You can have more capacity, but it tells you the limits on what you can put in them according to UL approval. You know, these are crimp type barrel connectors, or maybe you might call them stay-cons. These can be used on ground wires if you have a crimping tool, if you choose to crimp your grounds together instead of using a wire nut. So I've seen that on older wiring. And Jamie was talking about last night. He used to use these stay-con crimp connectors to do ground wires and not a wire nut. These are lugs that would be for your main feeder power coming in, possibly, that you would put a large wire in there and then use an Allen wrench to tighten that set screw. These are other types of crimp type connectors, ring tongue connectors, and fork type connectors that you would place the wire inside the barrel, use a crimping tool, the right kind of crimping tool with the right die position in the tool to crimp these. And the colors are going to give you, like for a yellow, if you help me remember, to get a kit, we have kits of these, and the yellow would be like for a number 12 wire through a number 10 that would fit in that yellow barrel appropriately, and when you crimp it, it's going to get a tight crimp on there. The blue is going to be for a smaller range, and the kit that you have when you open the lid tells you that blue will work for these different sizes of wires, AWG sizes. The red goes down even smaller. So, you know, for a really small wire, you don't want to use a yellow, because even when you crimp it, it's not going to be a tight grab on the wire. So go by the chart in the kit that you use, or the package that tells you the wire size range you can use with different colors of these crimp connectors. Cable types. Non-metallic sheath cable is what we're using in residential. It's called NM for non-metallic, NM, non-metallic sheath cable. Romex is the company, the earlier company that came out with it, and it's a trade name of a company, and everybody calls it Romex, even though other companies make the wire other than Romex company. When you go to buy the Romex wire, there's different suffixes on there. If you get an NM non-metallic type B, it's for dry locations only. You know, that's what we're using. That's what I order NMB. And you can see it, if you get a long enough piece, you can see it on their stamp somewhere. If you buy, if you're in an area that has damp location, maybe down the beach, then the NMC-B, you would buy that kind of wire cable. It has flame retardant, fungus, and corrosion resistant non-metallic outer jacket. The NMS-B is used in new homes with automation systems, and it contains your power wires, your power conductors, telephone wires, coax cable, everything in one assembly. I don't really know if I'd like that or not, because if something happened there, you would really have a major issue. It would affect everything in your home, but they do make it. I don't think I would buy it though, personally. Here, underground feeder cable is called UF, not in it. So in the it has a gray colored jacket to it, so it's not going to be the tan. If you get a number 14 in UF cable, it'll be gray. It's always going to be gray, that I remember seeing, and it's got a very tough jacket, so it's a lot harder to cut than the regular non-metallic NM type cable. It's very tough. This can be direct buried in the ground. So, you know, if you go like 18 inches down for trenching to go out to a utility building, you can direct bury that. Okay. I don't recommend direct burying cable ever. I always recommend doing it in conduit because Monday night I was teaching a class for Murphy Family Ventures that do hog farms. And that day on Monday, they had a part of a hog house that didn't have power because of a direct buried cable that was about 250 foot long, that it was shorted somewhere in the ground and they didn't know where it was shorted at. And could you imagine having to go up and dig up 250 feet to try to find one little section that's shorted out underground? So if you're going to do underground, what I would do, definitely, you know, run PVC conduit. Go ahead and run some 2-inch conduit from your house out to your building. If you're going to do a workshop, I wouldn't direct bury it myself. I would run conduit and then pull that wire through there, and then it's going to be there. You know, you're not going to have these issues of the effects of the environment on your cable over the years. If your conduit is glued properly, it's going to be sealed. Okay. And by the way, if you are doing conduit like that, once you get the conduit run, you can go on one end of it and take a vacuum cleaner, a suction vacuum cleaner, put a vacuum cleaner hose in one end of the conduit, and on the other end, you get you a grocery bag, a plastic bag, and you tie some nylon cable to it, some nylon twine. You got a big roll of twine you can get at Lowe's, and put the grocery bag in the conduit with a nylon wire tied to it, a really lightweight nylon wire that's strong enough to pull the wire, to pull your cable. But get nylon twine, tie it to a plastic Walmart bag, and let the vacuum cleaner pull that bag through the whole run of the conduit. And that's a cheap way of getting you a pull cable. Once the bag gets suctioned through all that conduit and it gets out the other end, then you have a way of pull your electrical wires through the conduit. And so it gives you a good pull wire. But by nylon, you know, twine that's pretty strong. And then also they got a type of a lubricant that's like a soap that's made for wire. As you're pulling it through there, you can put a little bit of it on the jacket of that wire, so it's going to be slick going through your conduit. And that's going to make it much easier going through your bends as you're pulling wire underground. We got some of that lubricant here at the shop if you wanted to see it, or when you go in Lowe's, I think they sell it in there too. Armored cable has the metal jacket on it, and they make an AC type and then an MC type. Armored cable and metal clad cable. Some locations here in the U.S. might not allow you to use NM cable, and you might have to use this flexible armor type cable in a house. Okay. I actually heard of a guy here not too far from the college. He's got his own security business. He does security systems. He built a house, his own house, and he actually wired his house. He didn't use NM cable. He used the metal clad cable, like flex conduit. He used it throughout the whole house. That's what he wanted to do for you know, to be safer. And that's what he did. He put the money in it and did it himself by his own choice. The AC type cable is also known as BX cable. And this is what it looks like. And you'll see that used in some places here in our shop on emergency lighting. You can notice that in commercial, like in Walmart, when you're in Walmart and you see power that goes to some shelving, like for televisions and all, in the electronics department of Walmart, if you notice, you'll see that type of cable in there that goes to their receptacles, to the regular 120 receptacles. They've got that type of a metal jacket around their wires. And the AC type has paper coverings around the wires You peel that off, and then you see your regular, regular insulation on the wires. And then on the EMC type, you got a clear plastic shield around those inside there. Service entrance cable, like your main cable that will come into a house, is called SE, and then USC will be underground service entrance. This can also be used on ranges and things like that in a house. So that you get into larger type cables there. And if you notice there, you see aluminum. You have the aluminum, that gray, shiny look to it. It's either aluminum or it may be a mix of copper and aluminum, but that looks like pure aluminum there. Service entrance underground. Then you have a SER. It's got 4 conductors instead of 3. And then the USC underground service entrance, it has a insulated ground there. There's different types of fittings, like you're using here at the school. You're using those Romex box connectors there, and there's different types of those. You have connectors that are for solid conduit. You were bending conduit last night here at the school, and so those are conduit box fittings for solid EMT conduit, for instance. And you can notice those in our shop, the different box connectors that are needed to tie to a box. On staples, you can do the regular metal staples like what we use here, and also they have insulated staples. So they got metal staples that have a plastic guard in there, so that when you do staple down to that cable, there's no way for the metal part of the staple to penetrate into the cable itself. So you have that little insulation in there, and that's safer. You pay a little more for those staples, but they make them that way. Those are also completely plastic there. There's metal straps, and then you have mounts there that can have several cables slid in those dividers there. They make those cable stackers. Raceways is defined as metal or non-metallic material that will hold wires or cables. That we can call it conduit. Conduit is raceway. And we're going to continue and try to do maybe like 1 bend each week on conduit. These are conduit straps. Grounding bushings there, that's like a lock nut that goes on threaded conduit that has a ground connection on it for grounding the conduit itself. And there's a coupling there for threaded conduit. Rigid conduit, you actually thread it. I could actually let y'all do some conduit threading if you wanted to, even though it would be, I've never heard of it having to be done in residential, because the rigid conduit, the thick wall, is used in industrial. It's the only place I've ever seen it used. But the rigid metal conduit is called RMC. And then if you go from rigid down to one that's not quite so rigid, it's called intermediate metal conduit, not quite as thick, IMC. So if you go buy conduit or order it, you would, it would be RMC for rigid, IMC for intermediate. And the fittings are going to be, you need to buy the right fittings to go with that conduit. It's rated for it. What you're bending here at the school is called EMT, electrical metallic tubing, and it's a thin wall galvanized conduit. So when you buy straps and buy couplings and you buy box connectors, you want to buy EMT fittings that's going to match, that's going to work right with the thickness of the EMT conduit. If you're in hog houses, for instance, they don't use metal, they use PVC. Okay. If you're on farms, chicken farms, hog houses, whatever, it's going to be PVC, so it can be waterproof. And here they got bell ends on them that you can slide another piece in there, you know, glue it with PVC glue. You get plastic straps, plastic box connectors that are glued in. Everything's glued in, except on the end where it ties to the box, it's threaded, and it's going to thread into a PVC box, and you can put some thread tape on there like Teflon tape to seal the threads to make it waterproof. Or, you know, you may be using the PVC conduit if you're doing outside receptacles at your house. You know, that would make sense there. You know. FMC, flexible conduit, is flexible metal conduit, FMC. You got certain fittings that have to be bought to match that, that are listed for that. Everything you're looking at, you can go to Lowe's and see every bit of it on the electrical aisles. I would encourage you to do that when you got spare time. Go in there and see what's right here in town that you can get to. Also, Sheely Electric, that's over beside Pizza Hut on 701 Business. Sheely Electric, they are an electric supplier. That's all they do. They're a supply house. Now you can't walk in there and see everything that they've got. A lot of it's back in the back. You got to tell them what you want, they'll get it out. But Lowe's is where I go for most things. You know, you can go in there and see everything, faster. And Lowe's is open later hours than Sheely is. And on Saturdays, Lowe's is open 7 days a week, where Sheely's not. I think Sheely's probably just 5 days a week. This type of conduit here, the blue hose, they call it Smurf hose, and sometimes, but it is a real thin, kind of flimsy conduit that you see used on fluorescent lighting. If you have the ceiling tiles that you can lift out with a fluorescent lights, like in our classroom here at school or in certain places that are using a suspended ceiling. But if you raise those tiles and look in there, you'll probably see that blue type ENT, electrical non-metallic tubing. And the ends there, you just push the conduit and it just kind of locks in, and it's kind of flimsy stuff, but that's what they use for fluorescent fixtures typically. When you get down into a more heavier type of a flexible conduit, you get liquid type metal, flexible metal. That's LFMC. And that's what you see used outside your house on your heat and air system. So what goes from your house out to your air handlers out there is going to be this, because it is liquid type. It's got the plastic washers there for your box connectors and everything, and it's rain tight. It has a metal jacket in there inside of the plastic there, so it's metal reinforced. The bottom kind has no metal in it at all. It's purely non-metallic, but it's fairly rigid. It's good in most cases, unless you got a risk on something hitting it, like in a plant. If you're concerned about something hitting it, like a pallet jack or something, in a plant, you wouldn't be using this type of non-metallic, because it's pretty stout, but it's not as strong as the metal reinforced type here, just metal on the inside. You got to get the right kind of fittings for whatever conduit that you're using on flex conduit. So, up here you got metal fittings for the metal reinforced, and then all plastic fittings for the non-metallic. For devices, we're going to be looking at the different switches that we use in residential, and a device is something that carries the current, but it doesn't use it. Switches carry current to a light. A switch is considered to be a device. A receptacle is an attachment plug or a lamp holder that you screw a light into. A receptacle would be installed in an outlet box, and it would be to accept an attachment plug. Many people refer to a receptacle as an outlet, The box is the outlet. That's where you can get power from. But if you put a female receptacle in there, it's considered to be a receptacle, you know, and that would be a receptacle outlet box there. Your duplex, it has 2 plugs on it, and there goes your terminals, as you already know what they are. The screws are 632s, by the way. You see the UL label there. Your hot is the narrow one, and the neutral is the long one. And you know, brass is for hot, and silver is for neutral, and green screw is for ground. On the back side of your duplex, it actually has a strip gauge. It'll tell you how long to strip the wire, a recommended strip length. The holes in there, I don't recommend using the push ends in the back. Some people actually, on some things, you may see holes in the back of your switches. You can just push the wires in without bending them. I don't recommend using those push-in holes, because over time they can become loose. I always recommend hooking your wire and actually putting it under the screw head. Tamper resistant is something that's required in most areas in homes now. Let's go to the book here. And it'll give you a code reference there on your tamper proof. In general, a tamper proof is one that you can't, a child cannot put a paper clip or something like that in there. You have a plastic shutter window in there that you can't stick just one thing in there. The shutter's open whenever you plug the plug in there. You got to have contact with the prongs with more than one thing in order for the shutter to open up. It's inside there. And so these are, even though we're not using these on your labs, take a note on there. That's what you're supposed to put on new installations. And if you're replacing a receptacle at home, you would want to use those type, particularly if you got children, because you know how kids are. Some kids are real curious, and they'll cram something in there and they could get electrocuted. So the tamper proof is on new house wiring, has to be used everywhere. The only places you can't use them is in a concealed area, like for a microwave or something like that, or for a refrigerator that somebody cannot get to. There's code references on that, and you got to look at the exceptions to know where those few places that you don't have to use a tamper-proof type. We won't take time now to elaborate on that, but if you're curious on the specific areas of the exceptions, we can get into it in the code book if you're curious. Now, ground fault, the GFCI receptacles, that's something you're going to wire in our class, and they have a test button and a reset button. You can hit test to make it trip, to make sure it will trip, and then reset to clear the fault. You know. And we're going to discuss in our class the difference between the connections on here. And let me see if I can enlarge. I think I can enlarge it and do something here. I'm going to show you some writing on the back of the receptacle. Uh-oh. Just lost the lost my page. Bear with me a minute here. Let me get back to where I was at here. Let's go there. Now we're back on target now. So hopefully you can see, and let me make sure you can see this. I'm going to stop this. I'm going to resync my screen here. Make sure you can see this good. Okay. On the back of a GFCI ground fault receptacle there, on the back of it, you know, on the side, you know, you'll have two brass on one side and you'll have two silvers on one side. You know, two hot screws and two brass screws, of course. But they're not the same. So if you look, the top two, it says with the bottom two says line, and there's a place to insert your wires in there without bending them. Now here, when you insert a straight wire in there of the right strip length, when you tighten the screw up, it actually tightens a clamp that really does clamp it with a clamping action. It's not like a spring type grabber in there. So for the GFCIs, you're not going to bend a hook and hook it around the screw. You're going to strip it a certain length, and there's actually a strip gauge on the back of this that tells you how long to strip them. There's a strip gauge on. This has got writing on here. I'll show you in person. Actually, right down at the bottom, you see the bottom. There's a strip gauge down there that tells you how the length to actually strip the wire and leave the wire straight, insert it straight into the hole, and then you tighten the screw and it clamps it. So, but my point is this: for a GFCI receptacle, when you come from the circuit breaker and you're going to feed that receptacle, you feed the receptacle on the line terminals. So you're going to put your hot and neutral down here where it says line, and the load is only used, the load terminals are only used. Now, when you hit line, you go into line there. Here's the difference between this receptacle and a plain one. When you go into your line terminals here with your hot and your neutral, the line terminals internally feed both top and bottom. So inside there, they're automatically hooked up when you go into the line connections here. Now, some receptacles say line at the bottom and some say line at the top. You got to go by the writing of whatever company that made it, because all of them don't put line on bottom. Some of them put line on top. But your breaker's got to feed line, okay, to go into the circuitry inside of here that's like a protection type circuit. The only time that you ever use the load terminals is if you're going to do this. If you're going to go and leave a GFCI and then leave it and go to a regular receptacle, and you want the regular receptacle to also be monitored by the GFCI protection circuit here that's inside that, then when you leave the GFCI to go to a plain receptacle downstream, you would leave out of the load terminals. You leave out of the load terminals, and then you're allowed to go to a regular plain receptacle like that. And then the regular one, if it gets a ground fault, the one upstream from it knows it because of the sensing circuitry in here. And this one's going to trip, and this one will be dead, and that one there will be dead also. So they'll both be dead because of the way you have it hooked up, okay? Now, if you're going to do multiple GFCIs that are the same thing, GFCI, and you want those to be independent, you don't want to have, if one trips, you don't want all of them to trip, then here's what you do. You go from your breaker panel and you go into your line terminals here. You have a set of holes here. So put your hot and neutral in one set of holes, and then get your next cable, going to go to your next box, to your next GFCI there, and take your next cable and go in hot and neutral there out of line, and then tighten your screws up. And that way you got the breaker feeds line on this one, and then you go out of line into another GFCI and feed into line, and then both receptacles have a direct connection with the circuit breaker. And if the first one trips, it doesn't trip the second one. Okay, so if you got, if you're tying these together, tying bathrooms together, you don't want one bathroom to trip and it tripped the other bathroom, right? Or outdoors, you don't want one receptacle to trip all of them, so you want to go line, line, line. You know, when you daisy chain them, that's why they got double holes in there, that you can daisy chain line and then tap line and go on to the next line and so on. If every one of them are GFCIs, okay, I just figured I'd throw that in there. You know, if you use the load terminals, then the first one in the chain, if it trips, then everything is going to trip downstream. You know, it's all going to be affected. You're going to lose everything at the same time. All right, now let's go back to I'm going to reseek the screen and make sure that you're still seeing what I'm seeing. Okay. There's a new type of receptacle out, fairly new, that looks just like a GFCI, but it's called arc fault. Now, arc fault receptacles are invented because of this problem here. Let's say, for instance, that you have a maybe you had a staple that was driven too hard into that cable, and it didn't trip a breaker to begin with, and it never really tripped the breaker, but that staple was driven in a little too hard into that cable, and over time, well, it actually punctured the insulation some when it was installed, but it didn't show up as a problem to begin with, and maybe a year down the road or whatever, the insulation, as it deteriorates from where it's been cracked, develops a little bit of arcing in there. So maybe, you know, maybe you've got these wires here arcing together a little bit inside the cable assembly, possibly, and it can happen. So if you have those actually arcing together a little bit in there, the arcing can be a fire hazard, but yet the arcing may not be a high enough current to actually trip the breaker. So here's where there's been house fires because of conductors arcing together like a little spark plug, you know, sizzling there, but the arcing current was not high enough to trip the breaker. But yet you had a house fire, and you had, you know, property damage. People could die over something that a breaker is not capable of tripping on. So they invented arc fault receptacles and also arc fault breakers. This is an arc fault breaker here that you're going to wire up here at school. It's got an extra little wire on here, a neutral wire. This breaker would protect the entire branch circuit, to where the one on the screen there is just going to be for one location. It looks like a ground fault, but it's an arc fault, and it says that on there, AFCI. So here's what the arc fault, here's what it can sense. It can sense parallel arcing. Parallel arcing would be this. It's if I had a hot wire and a neutral that were arcing together in a cable assembly, or in a box. If you had a wire to pop off in your receptacle box or switch box, and those two came together somehow, you know, or maybe whenever you strip the wire, maybe when you strip the jacket off of there, maybe you nicked into both of the wires and didn't know it. So whenever you cut the sheath back, kind of eyeball it and look, see, did you nick them? Because if you did, and then you go stuffing the wires in the box, here's what can happen. You can end up with some arcing in there, parallel arcing, because of where your wire strippers is cut into the insulation. That's called parallel arcing. So an arc fault breaker can sense it. It can sense small amounts of arcing going on, and it's going to trip. Okay. Now, series arcing is this. Series arcing would be this, is if I had a loose connection, if I had a wire here, but it was loose, and the loose connection began to arc. Okay. When power goes through the connection, and if the screw is loose, what can happen is it can actually arc. And that's a series arc whenever you have a connection, you know, maybe a hot wire, and that hot wire breaks and makes in line with one conductor. It's a series arc. So if you got a loose connection that's doing this, making and breaking like that, it's going to have arcing going on, and it's called series arcing. So that arc fault breaker can sense that also, and it can sense if you're arcing to ground, arcing to neutral, or a loose connection. Okay, so what's required now? All of your areas in new houses now have to have arc fault breakers. They got to have the arc fault breaker installed in all of your locations except the bathroom, and the bathroom has to have the ground fault. Okay. Now to show you how the arc fault hooks up, the arc fault has a neutral wire that ties to the neutral bar, and on the breaker itself, it's got two terminals. So the terminals on the breaker, you have a silver terminal and you got a brass terminal there. So if you're wiring up receptacles to an arc fault breaker, you're going to take your hot wire and the neutral, and they both go to the breaker. Got two screws there, see that? So the breaker actually monitors the neutral and the hot, and then then this embedded neutral wire goes to the real neutral bar in your panel. So your circuit neutral has to go through the breaker so it can actually monitor that line and the hot wire. And then, this pigtail that's built into this thing, it goes to your neutral bar. And that's something you're going to wire up, pretty soon. All this talking, I'm getting dry mouth here. Okay. We're knocking out, we're knocking out a week of lecture here in one sitting, and you can split it up, watch it in portions if you want to. That's fine. But try to watch the entire thing, because I'm taking a risk here of doing it pre-recorded, and I don't really want to do it, but I think that's the best thing to try right now. And you ask me if you have questions. So arc fault breakers or receptacles have to be used in all of your living quarters in the house, living rooms, bedrooms, kitchens, everywhere like that. They got to be used either in a breaker form to protect the whole branch circuit, preferably that way, because it's going to protect all of the wiring, the branch circuit, everything. Is the ideal way to do it. And then you've got an arc fault breaker here that could serve regular receptacles, and then it's going to be cheaper doing it that way. But again, arcing won't necessarily draw enough amps to trip a regular breaker. It may not draw 15, 20 amps. Arcing can generate enough heat and cause a fire and be way below the trip setting on a breaker. Okay, that's the whole point here. So other types of receptacles, you have the large ones there for your dryers, your stoves. This is a handy chart. This is one that you might want to take a snapshot with your phone, a picture. This really, it tells you the NEMA number, and NEMA is your National Electrical Manufacturer Association group. That they specify plug configurations, the way the blades are turned, and the actual configuration of the plugs for different voltage and current ratings. And every rating, when something changes on a rating on a plug, they change the blade configuration so that you can't put the wrong thing in the wrong hole. Okay, so this covers when you're going to order receptacles, like what I have to do. Instead of me going down with the school, I can't go down there and buy something and bring back. I've got to order it. So I've got to know when I'm going to order a 120 volt male plug or receptacle, I've got to know the NEMA number. Okay, and that's where you get all this information right in here, is for whatever voltage and amp rating. If it's a receptacle, you have here, and the plugs that are here. So if it's a 15 amp plug, these are the possibilities: 15 amp receptacle, these are the possibilities. At different voltages, 125 volt, 250 volt. You know, here, you know, you got a standard 15 amp female receptacle. 125 volt is a 5-15R. The male plug would be a 5-15P. So the P means plug, and then the R means receptacle. So that's how you get, if I had to order, you know, the females, it'd be a 5-15R. The male plugs would be a 5-15P. And then so on. You get down to the larger ones, but anyway, that just gives you the whole picture. You know, for larger ones, the 30 amps, that would be in there for, you know, your dryers and so forth. That's a regular single pole switch like you're using. You know, it's got 2 brass screws and 1 ground. That's your circuit. This is a new one. You're going to wire this on a lab. It's called double pole. You hadn't looked at that yet. That's one that's going to be way on downstream in our labs that you will wire. It's got actually, with this one, it shows 2 brass and 2 black screws and a ground screw. Now, what it's used for is for an electric water heater, for instance, to where you got 2 hot wires, and both hot wires need to be switched at the same time. So here you got 2 switches that when you open it, they both open, and then when you close it, they both close, called double pole. And your a circuit for that could be like here. And so this one has a 240 volt feed coming from your main panel, which will be coming from a double pole breaker, by the way, 2 hot wires. And they've re-identified a white wire. They're not using white for neutral. They put black tape on it. So you can do it if you re-identify. And they got actually 240 volt going, feeding into the switch, 2 hot legs, L1 and L2 feeding in, and then those 2 leaving going to a 240 volt receptacle. And that's where, you know, a water heater could be plugged in, or a water pump or something like that. Or air compressor, a 240 volt load. And so that's a special switch, you know, that you will wire up. I've got one here, as a matter of fact, and all of these are brass. So you know, the tops could be incoming or the bottom. You can feed in the bottom, leave out the top, or vice versa. But the bottoms is a pair and the tops is a pair, you know. And it's a heavy duty switch there. So it's one that you'll wire up. This one has you strip the wire straight and push in, and you tighten up a clamp. It actually has a saddle clamp in there, but you don't really bend the wires and hook them around that one. Water heaters, if you have a plug like that in there, you're able to disconnect it when you're going to service it, replace a heater element in there, and that's a safe way to have it, so you can actually unhook it at the location where the water heater is, or water pump, for instance. It can be unhooked. If you don't do it, if you actually hardwire a water heater, then the only way you can cut it off is go to the breaker. And the way things are nowadays, you've legally got to be able to lock out that breaker with a lockout device before you service the water heater. So you either got to have a lockable breaker, a lockout device, or a receptacle that it can be unplugged within the view of the person that's doing the work on the water heater. 3-way switches are something that you're going to start to get into. Justin and Darren are starting that lab now on 3-way switches. And if you notice here, this switch has a common terminal. It's a black screw, and then 2 brass terminals that are called travelers. And there's a ground screw. Now, you use 2 of these switches if you're going to control a set of lights from 2 doors, like in a large kitchen or a room or a shop door. You can actually control the same lights from 2 locations. You use 2 of these 3-way switches at 2 doors. So you don't use a single pole switch if you're going to do 2-door switching. And here goes the circuit. I'm not going to elaborate on it, but you come in from the breaker panel to the first switch, and your main hot wire feeds into the common there. So the common wire, the black screw, is an input to that switch. And then the travelers are the outputs. It's two outputs, and they both can be hot, but neither one of them is always hot. Always one or the other is hot. So this switch, that common, that hot wire is always connected to either the red or either connected to the black, depending on the position of the switch. So there's always a hot traveler leaving there. The switch is never totally off. On the front of the switch, you're not going to find the words on and off. It doesn't say on or off on the switch because up can be on or down can be on based on the position of the other switch. You know, sometimes at your house, if you have this, sometimes down can mean the lights are on, depending on the position of the other switch. So they don't print the words off and on a three-way, but it takes two of those to do this. The cable that goes between the two door locations has to be, in this case, a free conductor. So you've got to have that extra wire in there if you're going to do three-way switching. You got to have that red in there, so it's going to be a 14-3 in this case. In the drawing there, it's a yellow that's a number 12. So it's a 12-3 there going between the doors. So here, you're going to leave the two travelers there with a red and a black, and they're going to go over and meet the travelers of the next door location. So the travelers, these are outputs going to the next door, and over here, the role of that switch of those travelers is to receive power. So you're going to consider those inputs. And it's the same switch, but they're used in reverse. Okay. So here, these two travelers are considered the inputs. And so you got red and black that left the first one is going to the brass terminals on the second door location. And they're considered to be two inputs on that switch. And then the common, the black screw, is the actual output on the second door. So you leave that black one, and it goes out to the terminal, the hot terminal on the fixture. And then the neutrals are continuous. You don't interrupt those, so the neutrals tie together. You don't break those. The grounds, they get pigtailed to the straps, and that's the way you wire, okay? And with this, the way the circuit functions is that you can cut the lights on or off from either location always. You've got full control from either door, regardless of the position of the other switch. Now it may force you to flip a switch down to get the lights on, but you're always able to make them go on and off from either location because of the design of the switch that it is. And the insides of the switch is called, it's a single pole in and double throw leading. So the power on that first one, it goes in there and it actually toggles between the two outputs that leave. So it's a single pole in and a double throw leaving. That's what we call it. Another term for it is a single pole in, double throw leaving. Okay. And as far as understanding what I'll do here at the shop, I'm gonna show you on a board. I'm gonna get on a large dry erase board and draw the insides of the switches and show you logically how this circuit works. I won't go into it here, but we're going to do that in person. I'm going to show you in person how the internal guts of the switches work as a whole, and you'll see it logically how it works, you know, how it does what it does. On the cable diagram, you'll notice up here, the arrow means home run or breaker panel. And the two lines on that cable means it's a two-wire cable with a ground. S3 means it's a three-way switch. And the next cable, it's got three insulated conductors and a ground. So it's got three lines, three-wire cable ground. S3 is a three-way switch. The two lines mean there's two wires in the last cable with a ground. And then there goes the light fixture. A four-way switch is one that's used when you're going to go from a two-door location to control lights and add a third door to it. So if you're going to have three doors in a large workshop or a warehouse or something like that, or a hog farm, and not just two doors to control the lights, but three different switches to control the same set of lights, and all of them have full control on it. You take a switch that's called a four-way switch, and you actually place it between the two three-ways. So you always begin and end with a three-way, with three-way switches, but the center door, the number two door, will have to have a four-way switch in there. It's got, in this case, two black terminals and two brass and a ground. Now, the four ways that we have, actually the newer ones do have two black terminals and two brass. But there are some of ours in the shop that have all brass, that you may have four brass. If you got those, just realize that the bottom set is going to be a traveler set, and the top is another pair of travelers. And the way they wire up is like this. And also notice that on the four-way, they don't have an on and off designation, because up or down could be on depending on the position of the other switches. This is just this is the drawing of the lab that you're going to wire here on doing a three-location switching. And the only difference is they between a three-way and a three-way that you had on the previous circuit that we saw, they've gone in there and put a four-way switch between as door number two. And all it takes is this. You leave on the first door, you leave the two traveler outputs here with red and black. And you go into the traveler inputs on the four-way switch there with red and black. So those are your incoming travelers, and then your outgoing travelers are the black ones on the bottom here. That's your outputs, and then those two go to the third door to the traveler inputs over here, red and black. And then at that last door, of course, it's a three-way switch. It has to be. And then the common, the black screw, is the one that's the actual final output of the whole circuit that actually feeds your hot terminal on the light fixture. And that's a circuit you're going to wire up. There goes your cable diagram up top, and it shows the S4, a four-way switch in the center with the cable designations up there. That's the cable diagram is what you would get with a contractor, to where the pictorial wiring diagram you learned out here. And you really ought to be taking pictures in your book of these color shots and have all of these in your phone, so you can always refer to them on the job. And we're winding it down here. I know it's, I'm kind of long-winded, but I'm covering the equivalent of two evenings of lecture. You would really normally be here 4 hours a night. You're here 3 hours. So these 2 hours that you're missing, we're making it up by doing this. So anyway, we do what we got to do. You know, I'm just thankful that we can be on campus. I thank God for that. You know, and glad y'all are back. So here you got dimmer switches. You know, they got different styles, rotary and slider type. And dimmers can be single pole or they can be three-way. So single pole dimmers is what you're going to wire here. Well, I got some three-way ones also. If you got a three-way dimmer, well, that's actually not a three-way. That's got an in and out and a ground there. But they do make them a dimmer that'll work in conjunction with another three-way switch, so that you can have two location switching. But if you do that, then only one door can have a dimmer, and the other door's got to have a three-way switch. So if you want to replace a three-way switch at your house with a dimmer, you can do that, but you got to buy one that's got that extra wire in there that'll let it replace a three-way. Dimmer switches do have a wattage limit. So whatever the wattage rating is of the dimmer switch itself, you don't want to exceed that with too many lights. The only time you'd ever be concerned about that would be is if you had a lot of lights on one, and I doubt you do, but you would add up the wattages of all of your bulbs. Like if you had, you know, so many 60-watt bulbs, if you had 4 60-watt bulbs, for instance, then the 4 times 60 is going to be 240 watts, okay, total. You just want to make sure that the dimmer is rated more than 240 watts. Of course, it will be, you know. But whatever you're going to control by that, make sure that all of your combined loads does not exceed the wattage of the dimmer. Dimmers cannot be used on basic LED bulbs. If you go to, this ain't an LED bulb, but if you buy LED bulbs now, the cheaper ones may not be, they're not dimmer rated, so you can't run them with a dimmer, okay? But you can buy LED bulbs more expensive that are rated, that are LED, that are dimmer rated. So you can buy an LED bulb that is dimmer rated if it says it on the box, okay? I'll just say that. Combination devices give you 2 things on one strap or one yoke. So if you don't have room, or if you're sitting there with a single gang box but you need 2 things in there, then you're going to buy a combination device. You can get a switch and a pilot light. And here I've got one here that's actually a switch and a receptacle. So here you got a switch there, and you've got a receptacle on one yoke, on one strap. Okay, that's just showing you that there's a lot of variety of things that you can get on combination switches, devices. Specialty switches like for doorbells. They got some fancy decorative type overcurrent protection. You know, we got breakers in most cases. Single pole, double pole. They do make GFCI breakers. Like in my house, our house was wired in 1977, 78. And the breaker is a GFCI breaker. They didn't use GFCI receptacles. They got a GFCI breaker that's in the panel, and it protects all of your ordinary receptacles in the bathroom. So if you get one that trips, if you get a faulty hair dryer or something, or even something outside the house, like we got outside receptacles in both bathrooms, they're all tied to one GFCI breaker in the panel. So if you get a fault condition, you lose both bathroom receptacles and the outdoor ones at the front and the back door. You lose all that at one time. So the other breaker with the green there, it's actually arc fault circuit interrupter. And so that's one specifically for arc fault. But now you can buy both combined in one unit. It's a combination arc fault GFCI circuit breaker that does everything all wrapped in one. You just pay a little more for it. Fuses. The only time you'll see fuses nowadays on the installations would be for your heat and air units. Whenever you go outside the house, they might be using a fuse block. Maybe, maybe not. They may have a circuit breaker right there. Newer installations, you're probably going to see circuit breakers on there. But if it's older heat and air unit, you may see cartridge fuses in there. If you got a really old house, plug fuses that screw in like a light bulb. So for fuses, if you're going to test a fuse, I'll show you briefly how to test one. I'll cut this off. If you have fuses are very simple to check. I'm going to move the webcam where you can see what I'm doing. So on your meter, you're going to flip it to the horseshoe symbol for ohms. If I touch the leads together, you're going to hear it ring, and you're going to get a low number like 1 or maybe 0. Ideally, 0 is the best. You have the very low resistance in the test leads. Now, a bad fuse, here's how it's going to test. But to check one, and it doesn't matter what size the fuse is, they all test the same way. You can touch one side of it, but you can't touch the other side, or it may feed through your body and get a false reading. But I'm checking it here with the ohm meter, and it says OL, or over limit. It means it's over the limit of that range, which is 1 kilo ohm or 1,000 ohm. So it's bad. A good fuse ideally is going to give you the reading of leads that just touch together. 1 or 0. Okay, here's 1 ohm that the test leads have. So I can look for 1 ohm roughly here. All I'm doing here is I'm contacting one end here, and then I'm going to touch. But see, I'm getting 1 ohm there through the fuse. It's the same resistance as just touching the leads. 1 ohm of the test leads, and then the fuse is also giving me a 1 ohm, and I hear the ringing there. So that's how you check it. If you're checking, you can also check circuit breakers the same way if they're out of the circuit. It's gonna check like a fuse. So if I have a circuit breaker that's pulled out, that's just sitting out there, in my hand there, then I can go from the clip, the spring clip that goes into the panel. I can actually go into there like that, and hold the meter in there, just like so. And then I can come around to the terminal that you tie to with your wires. So I've got one on the spring clip that goes on the bus bars in the panel, and then the other one I got here. And I'm going to the lug, and it's not ringing because I got it off. I go on with the breaker, and it rings. So right now I'm getting 1 ohm through the breaker, and you hear the ringing sound. That's with the breaker on. With the breaker off, I get an OL. I get a over limit. So we're checking continuity through the breaker the same way as you do through a fuse. You're looking for a continuous connection that should be the equivalent of the leads touching together that says the amount of resistance in the test leads. You can know that out. Okay. Now, if you happen to be go back to the book. If you happen to be checking a screw-in, a plug type fuse, it's called Edison based, then what you would do, you would check it like you would. I'll just show you with a light bulb how you would do it if it was a fuse. Now the fuse plug, it screws in like that. It's got threads. If you happen to run across the old one like that, here's how you can check it. I doubt you will, but you don't never know. You put the meter back on ohms. I love this camera we got here, this webcam. I can move it and set it where I want to. Thanks, Barney. Touch your leads together. Make sure that it rings good. And look, you would go here to the threads and pinch it like that, and then touch the tip. Now, this is a light bulb here, but I'm talking if it's a screw-in fuse, do this. Go to the threads, and then go to the tip. Now, here I'm getting 17 ohms there, but look, we're talking a light bulb that's got resistance to it. If it's a screw-in fuse, you're not going to get that 17 ohms. It should be like way down around 1 ohm or so, or maybe 0. So anyway, that's the way you test it. It goes, the threads and then the tip is how you do it. Okay. Figured I'd throw that in. Move my camera here. This camera is cool, man. You can really put it where you want to. It's got a manual focus on there. It's really nice. I really appreciate that. Barney got me I got an extra one today. I got one here at my office, and I've got one at home, so I don't have to drag it back and forth now. So I got an extra one today. So Barney, he supports us great. I'm telling you, he really does. He don't mind spending money if he's got it. He don't mind signing off on what I need. So thank God for him and for Katie. Let's see. Let's go back. We're almost done with the book. I know you're probably saying, well, when is it going to get done? Ain't he done yet? Well, here we go. I don't want y'all missing anything. I want you to get your money's worth. I want you to be fully qualified when you finish this course, that everything that you're supposed to learn in here. And if you really want it, then you can get it. Okay. I'm not gonna. I won't intentionally shortcut you on anything. I'm not perfect, but I'm not going to intentionally shortcut you on anything. I want you to be safe out there, and hopefully one day that you possibly may get electrical license yourself, possibly. These they do make adapters down there for some of these screw-in type fuses, and that we won't get into all that. You can read in the book on that. Let's go. Those are different size fuses, and they have some of them. If you notice on there, it says the word time delay. The time delay is for motor type loads. So if you're using fuses on the heating and air system, it needs to be time delay for sure, because you got fans that kick on. All your motors have an inrush current that goes, 300, 400% of normal when they start the motor up until it gets up to top speed. And then once it hits top RPM, then it levels back down to your regular amps that's on your nameplate. So you got to have a time delay on a fuse, or it's just going to pop as soon as the motor starts up. So it's a little more forgiving there. If you get a fuse that doesn't say time delay, you can have them that say one time, and then these just say like class. That says time delay. And these other ones don't say that. So if it doesn't have a time delay to it, you don't want to use it on a motor. You could use it on non-motor type loads that don't have a high inrush. There's a voltage rating on them also, 300 volt here. Some fuses are 600 volt. Here you got load centers and panel boards. The load center, you can put your breakers in there, and also has the main disconnecting type breaker up there up top that can disconnect the whole panel. This is one that doesn't have the main breaker in it. It just has main lug only. So, your power comes in, you got your individual breakers, but there's no main disconnecting means there. Safety switches, you can see those on heating and air units in residential, and it would be a service disconnect for your air handler, possibly. Inside that, it might be plain switches, or it might have fuses in there as well as a switch. It could have a switch, a breaker that's a switchable breaker, so it may be a breaker type disconnect. That's a breaker type disconnect there. Fasteners, a variety of nails that are used in residential. Some of them are like finishing nails for doing whatever. There's all kind of different nails. Anchors, there's different kinds of things. If you're going to hang something on sheetrock, there's a variety of anchors that are up top. And honestly, the best thing I've seen on sheetrock, in my opinion, would be the ones, the spiral type right there. They actually screw into the drywall, and they hold really well. And you don't have to, these toggles here, if you drill a hole and put a toggle through there, it's going to go through and then spread and come back. You got the risk on that toggle coming loose and falling in the back. That spiral type deal there is the best thing I've seen for drywall. And let's see if I can, they got them at Lowe's. I'm gonna try to let's go back. I just lost the screen. Let's go back up and try to get right. I'll show you something here. Yeah, right there. This shows you the spiral sheetrock anchor, and it works very well. All you got to do is you just tap that in a little bit with a hammer, and then just start turning. On the face of it, if you flip it around, there's a place for a Phillips screwdriver, and it goes right in that sheetrock so nicely. And there's nothing metal in there. It's all plastic, so you don't run the risk on screwing into a wire or something beyond a drywall that you can't see. So there's no risk there at all of penetrating a wire that may be behind that wall that you can't see. These, I don't like them. There's a risk on you getting behind in there and clamping on the wire. Maybe, maybe not. You don't know unless you get one of these devices out now. And you can Google. They got something called. You guys get on there. Get on YouTube and look up something called Wallabot. Wallabot is something that it mounts. It sticks on the back of your cell phone, like on a smartphone. And what it does is it allows you to take your phone and run it across the sheetrock wall along there, and it shows you a visual of actually what's in the wall. It'll show you if there's electrical wires in there or pipes, and wire shup is one color, pipe shup is another color. It's called Wallabot, and you can buy it again, and it sticks onto the back of the cell. It's amazing, really, what it does. And I haven't bought one. I don't do enough of that to really buy one, but you can actually see what's actually behind the drywall on your cell phone. It shows you a color-coded image. Pretty amazing. Let's go back to full screen. I'm almost done here. Appreciate your patience here. Let me make sure I resync here. I'm just about done. I'm getting pretty tired myself. I know you're tired of hearing it, probably. So this is different types of the tool that's used for installing anchors. You know, different types of drills. Different types of screws. You know, you've got wood screws, sheet metal screws, sheetrock screws, self-tapping screws. So, you know, if you're going to go into sheetrock, get a sheetrock screw. You know, if you're going to go into wood, when you go into Lowe's, as soon as you walk in Lowe's, go right straight ahead and veer to the left just a little bit, and you got a whole aisle of nothing but screws, fasteners, and they got it all. And, you know, be careful not to buy wood screws for sheet metal, and don't buy sheetrock screws for so on. If you're going to go into sheetrock or metal, you can actually get them. It's got drill bits on the end of them, and you know, get you an adapter on your drill, and it'll actually drill the hole and then thread itself. So it's a self-tapping screw. You know, here. Different style heads on fasteners that are nowadays. Torx is common on a lot of screws now, and they work well with drills. If you got a Torx bit, then those Torx head screws are good if you're doing woodworking and doing assembly work, something you're going to screw together. Torx is pretty good because it grabs good. It doesn't you don't have the problem with it stripping with the heads. Posi drive is a type of head that's used now on some electrical things. Posi drive, you get a special screwdriver for that. The square heads they're kind of, you can see those on some things, and it may be a square bit inside of a slotted bit, like on some receptacles that we have that have the square bit inside of a slot. So on those Klein screwdrivers that we have, the multi-bit ones that we have, you can look in this 11M1 that we have in our tool cabinet. It's actually got the square bits in there, and I've already mentioned that to y'all. So you can use those wherever it allows you to, if you choose to. Nuts, you got anchor nuts, hex nuts, slotted nuts. Slotted nuts, you would run a pin through it to lock it so it couldn't come off. It'd be a hole in the shaft, so on. Different kinds of washers, lock washers, cable ties, and that's it. Okay, so I'm through talking. Thank you for listening, and I'm probably not going to have this worksheet in there tonight. I know I won't, because I'm pretty pooped out. I'm ready to go home and eat. So I'm hungry, and I know you're getting hungry now. You've listened to me for quite a while. So this worksheet 2 I'll have it in there sometime this week, probably, and it may be Friday before I actually get it converted, because I've got to convert all of this, copy paste everything in there one by one, and create the worksheets that I've never done before in Moodle. So it's just kind of look for it, you know, later in the week. Tomorrow I know I won't have it, because I'll be teaching from 9 a.m. to 9 p.m. And so it may actually be Saturday sometime before I actually get it in there. So, you know, no rush. So we don't really know how many chapters we're going to be able to cover with this class the way we're doing it. I'm shooting for everybody getting every lab done and every conduit being done, and get however far we can in the book, and we'll just see how far we get. But I do want to make sure that you get enough shop time to where you can get every lab done, hopefully. Okay. So thank you for listening. If you got questions, let me know during class, or you can call me. You got my number, text, anything like that, and I'll make sure that we clear up anything that you ask about. But if you don't ask now, I don't know what's not clear to you, so please speak up. And that's the risk. The gamble that I'm taking with this is doing these pre-recordings like this and hoping that you're going to tell me if something's not clear. If you don't, I don't know, and I'm not. You know, that's the gamble, and I hope that this is going to work okay. Give me your opinion on how this is, and then I'll adjust things accordingly. You know, so thank you, and God bless you. Have a great evening, and I'm going to end the session, and then I'll upload to YouTube so this can be seen. Thank you, and I'll see you guys tomorrow night.